This is a short review of some of the thermodynamics you need to know to understand phase changes. To begin with, let's just think about a few simple questions related to enthalpy and entropy and free energy changes, comparing liquid water and gaseous water. So our first question is, which has a higher enthalpy? Liquid water, gaseous water, they're exactly the same, or it depends on the temperature. Now, I'm not going to give you lots of time to think about the question because otherwise you'll sit here and just stare at the video. The answer here is that the gaseous water has a higher enthalpy. Why is that? What in the world is the enthalpy? If somehow you've forgotten this, we need to have a refresher. And the easiest thing to remember is that the enthalpy is essentially the energy of our compound. Technically, if we have a process, the change in the enthalpy at constant pressure is equal to the heat. But for all intents and purposes, the change in the enthalpy is essentially the change in the energy for the compound. And so when thinking about this, we know that low enthalpy is low energy. And remember, low energy means stable. The lower the energy, the more stable. Things move from high energy to low energy spontaneously. High enthalpy is high energy. It's up at the top of the hill, and low enthalpy is low energy. It's down at the bottom of the hill. So what energy landscape are we talking about when we think about the difference between a liquid and a gas? If we imagine some kind of plot for this change, we have enthalpy, or the energy, as up, lower energy being more stable. And down at the bottom of the hill, we have our liquid. And the reason that it's lower in energy is the molecules are close together. Remember, all substances have intermolecular forces that are attractive. The stronger the forces, the more attractive they are, which means when the molecules are close together, they have a lower energy. Lower enthalpy compared to molecules that are separated. This is essentially just potential energy. It's the electrostatic potential energy. There's positives, there's negatives, there's electrons in the molecules, they're attracted to one another, and when they're close together, they're lower in energy. Contrast this with gas. In a gas, the molecules are very far apart, and so even if the molecule has a dipole moment or some big dispersion forces, the molecules can't feel these interactions because they're at a distance that's too large. And so essentially the molecules have no interactions, which means they're in a much higher potential energy state. You have taken them from this low energy point of being close together and you've ripped them apart. To do that, you have to increase their energy. So you go from a low energy state close together to a high energy state far apart. So comparing the two, we have molecules close together, attractive intermolecular forces, that's going to give low enthalpy, or molecules far apart, essentially no interactions, and that's going to be high enthalpy. If we look at this change, this would be the change which we would call the enthalpy of vaporization, starting from the liquid going to the gas. That change is then going to be the difference between the final state, the enthalpy of the gas, and the initial state, the enthalpy of the liquid. And so delta H vaporization we know has to be positive because the gas is higher in enthalpy than the liquid. That is, it requires energy to move from the liquid state up to the gaseous state. And that's because we're ripping apart those intermolecular forces. Remember, a positive change is always energy into the system. We start at low energy, we end up at high energy. That must be because we put energy in. It's endothermic.